Today, we have a new paper from the Baker Lab, which has just been published in Nature. This is a big one. They've designed proteins with deep learning, and these proteins work. It's a major proof of concept for computational drug design. But is this the end of the debate on AI's role in structural biology, or has the battle just begun? Let's have a look. The new paper is about so-called endocytosis-triggering proteins, ETPs for short. These are designed to bind to cancer receptors like 𝗤𝗓 and force them into degradation. You see, cancer cells often overexpress these receptors, which then become targets for drugs. One successful class of such drugs are small molecules that block the interaction of these receptors with their natural ligands. However, there are many more ways to interfere with these receptors, and one of them is to simply eat them. That's what the ETPs do. They tell the cell to eat them. Sounds good. But can an AI really design something that works? The proteins that the AI has designed show up as functional in live cells. And this is not just a predicted structure like we have seen from AlphaFold or raster. It's not just a static model. The design likely took into account molecular dynamics and binding interactions. Because these proteins don't just fold into a given shape, they also have to bind to other molecules, in this case, the target receptors. So if that works, then it's a major achievement. It shows that AI can not only design stuff that exists, but also that it can come up with something truly novel. This is a much bigger deal than many people seem to realize. I know that many of you are familiar with the recent push by the FDA to modernize drug development using AI and computer models. This is part of the FDA's Modernization Act 2.0. They explicitly ask for more AI-driven therapeutics because they can speed up drug discovery. And this new paper is exactly the kind of thing they are looking for. It shows that AI can help to develop new therapeutics without the need for animal testing. But now comes the part where some of you say, hold on, these AI models only interpolate, they don't extrapolate. So even if they work for this paper, that doesn't mean they can be generally useful, and you'd be right. An example for an excellent critical assessment of AI-based drug design came earlier this year from Dr. Sarfraz Niazi, who argues that the predicted structures from AI, for example, AlphaFold or raster, don't necessarily correspond to real-world function. He writes, 3D structure does not equal biological activity, and this is absolutely correct. Many things can happen between the AI prediction and the actual function of a protein. For example, post-translational modifications, PTMs for short, or the binding of other molecules. So he says, quote, AI models interpolate, they do not predict. And again, this is correct, but I think we tend to forget that the same is true for any kind of model. Any model that we build, whether it's an AI or not, only tells us something about the world if we have data for that. If we don't, it's just a fantasy. So yes, Dr. Niazi is right to be skeptical. But I think his critique ignores the experimental validation that the Baker Lab has done. Their AI designs were not just made to fold into a given shape. They were made to solve a specific task in a living cell. And to do this, they had to be validated in a wet lab. This is what often gets lost in the discussion about AI. Yes, it's a tool, and no, it's not a crystal ball. But when used with the right data and then combined with wet lab work, it can really help us understand and fight diseases better. In summary, I think both positions are right. The Baker Lab shows that AI can be extremely useful to design proteins for a given function. But Dr. Niazi is right that these designs only work if they're backed up by experimental validation. So let's keep discussing this and find a good balance between healthy skepticism and unfounded hype. If you want to learn more about how neural networks work, the Neural Network course will give you a deeper understanding of how intelligent artificial intelligence really is. And afterwards, you can continue learning more about your favorite topics in science, computer science, or maths. All courses on Brilliant come with interactive visualizations and follow-up questions. So go and check this out. Thanks for watching. See you tomorrow.